Hello, you're welcome to this video. In this tutorial, we are going to be discussing about how to find the acceleration due to gravity using a simple pendulum that is hung at an inaccessible height or hung from an inaccessible height. Okay, right. Okay, in the previous video, we talked about finding acceleration due to gravity using a simple pendulum that is hung on a retort stand. Okay, that one is just the tabletop experiment. But in this case, we have a situation whereby the pendulum bulb or the simple pendulum is hung at an inaccessible height, such as a ceiling. Okay, so we want to see if we can still be able to get the same value of the acceleration due to gravity using that kind of experiment. Okay, yeah. All right, so looking at this that we have here, this is a case whereby this is the ceiling, right? Okay, the stuff being hung at the ceiling, and this is the floor. So this is more like a room with the string, a long rope that is hung somewhere at the ceiling and then brought down to this equilibrium position. This equilibrium position is the neutral position. The neutral position when the pendulum is not swinging. Okay? All right. So let's say the entire height, I think, let's say the entire height of the room from the beginning to the end, let me just call that the entire height. Let the entire height of the room be h. Okay? So if the entire height, the height of the whole room is h, then let's say from here to here is small h. Okay? So from the ceiling to the floor is the big H. But from the floor to this place here, from the floor to the point where the pendulum bulb is suspended, okay, let's call it a small h, that is the height from the floor to the pendulum bulb. Okay, so that simply means that if we plan to know the height or the length of the rope or the L, which is the length of the thread, okay, or the string, if we plan to know that, then we will say that L is equal to H, like the whole height of the room from the ceiling to the floor minus small h, which is the height from this floor to the point of suspension, okay, of the pendulum bulb. That is the distance between the pendulum bulb and the floor, okay? So which means that the length of this thread from here to here, or from here to here, or from here to here, it's an equal length all through. So the length of this thread is going to be given as the full height of the room minus the height of the point of suspension from the floor. Okay, so that is that for that. Now, the same formula applies as the formula we used in the experiment in the previous video, the experiment of the simple pendulum hung from the retort stand. If you can remember that we say that the period of oscillation is equal to 2 pi root L over G. Okay, so the same formula applies in this case as well. L is the length of the thread. But there is a precaution that I want you to remember. You see, if you are performing these experiments in the lab, anytime you want to take the measurements, I know you must have been told in your lab experiment, okay, just a reminder, okay, that anytime you seek to measure the length of the thread, you don't measure it from the top of the bulb. No, it's not from the top to the point of hanging, but it's actually from the center of the bulb. So it is a standard that whenever you want to measure the length of the thread, you measure it from the center of the bulb, from the approximate center of the bulb to this place. One of the precautions, you don't measure from the top of the bulb. So please mind you. And that is also what is represented in this diagram, okay? Good. So, all that's been said, if we want to find the period of oscillation in this experiment, the same way is how we find the period of oscillation it's the same way for how we find it using the retort stand, like what we did previously. Okay, fine. Period is equal to 2 pi root L over G. And already we know from the initial explanation that the length of the thread from that inaccessible height to the center of the bulb is the same thing as the height of the room, the height of the whole room minus the height from the floor, okay, to the bulb. All right, so instead of writing this L, we just replace it to say T is equal to 2 pi, then root H minus H over G. All right, so T is equal to 2 pi root H minus H over G. Good. So if we want to proceed from here, the next thing is to square both sides like we did earlier. That's square both sides. So squaring both sides, we are going to be having, just continue from here. We're going to be having T squared is equal to 2 squared pi squared, okay? Then the square will cancel the roots, okay? So the square cancels the roots, keeping H minus H over G. So we square everything, okay? Square T, square 2, square pi, square this root. But the square over the root will cancel the root. And so it will now remain the property under the root, which is H minus H over G. Okay, so proceeding from here, we have it as T squared is equal to, mathematics permits us to expand the bracket, okay? Because the stuff here multiplies what is here and also multiplies what is here, okay? So which means that we can have it as 2 raised to the power 2 is actually 4. Then this is 4 pi squared, okay? So, excuse me, the 4 pi squared can multiply, the 4 pi squared can multiply H to give us 4 pi squared big H minus 4 pi squared small h over G. Remember, 2 raised to the power 2 gives us 4. Then with this pi squared, okay? So now the 4 pi squared multiplies H to give us 4 pi squared H. Then this minus is here. Then because plus times minus is minus, then 4 pi squared multiplies the small h to give us 4 pi squared a small h, okay? Then over G, okay? Good. So as we have it that way, well, mathematics permits us to share this denominator across these two stuff, because this is just like 7 as the lowest common multiple, like a common denominator and all. So we could share it across. So we have T squared is equal to 4 pi squared BH over G minus 4 pi squared small h over G, okay? Because if you find the lowest common multiple of G and G, it will be G. Then you say G and G 1 times 4 pi squared h, so it will give you back what is here, okay? So we can split the denominator across the two terms in the numerator. Very much allowed. Okay, so having done that, remember that we are considering the variable involved in this situation is that when you are performing this experiment, you will be changing the value of, you'll be shortening the rope. Okay, maybe you use the particular length at first, then you reduce it to a smaller length, you make it swing 20 times, okay, you record the time for the 20 oscillation, from there you get the value of period T as that time for 20 oscillation over 20, and then, and all that. So you keep shortening the rope and then looking for the time for 20 oscillation in each case, okay? Remember, you did all of these things in the lab, okay? So you're just trying to do the theory now for the sake of the exam you want to write. Okay, so, which means that the height of the room remains constant. What is actually changing is the height above the floor. The height of the room, which is the big H, is constant. The height of the room does not change. But the thing that keeps changing is each time you shorten the rope. Maybe you use a thread of, let's say 70 centimeters before, or a thread of 100 centimeters is what you used before. Okay, you reduce the length to 90, you reduce it to 80, you reduce it to 70 to 60. You just check about five different lengths of that thread. But what I'm just trying to explain to you is that as you keep changing or shortening the length of the thread, the height of the room remains constant. But the thing that is changing, or that is changing, is this small h. The small h is what is changing, okay, as you are reducing the length of the thread. So at the end of the day, we find out that the period of oscillation is changing based on the length of the thread, because the longer the thread, okay, the longer the thread, the longer the period, because it takes it more time to cover one full cycle. But when the thread is short, then it takes it a shorter time to cover the cycle. You get that? So which means the period of oscillation is changing based on the length of the thread. And another thing again that is changing is the height above the ground, because the length of the thread is shortening and that height will be increasing. Okay? Now, what else changes? Nothing else changes, because the height of the room is fixed, is constant. And then 4 is constant, pi is constant, pi is a constant number. G, acceleration due to gravity, is constant too, as expected. So, which means every other thing here is constant. The only things that are variable is the t squared and the height of the bulb above the ground. So, we have to now look for a way to make the variable to stand. Okay, we have all of the things here constant, and constant, variable, and then constant, then this. Okay, so which means if you compare this to the equation y is equal to mx plus c, if you compare it to the equation of a straight line, y equals to mx plus c, you will see that this one represents our y. Okay, this one, since everything is constant, then, so this represents our y, this represents our c. And then this one, the group of constants around here, okay, the group of constants around here represents the slope, because the slope is also a constant. Remember that from our second video. Okay, slope is also a constant value. Then we now have this one as the second variable, which is x. So, which means we are having something that looks like y is equal to c minus mx. So this is what we are having as our equation of a straight line. Y is equal to c, the intercept, 4 pi squared h over g, okay, minus mx. That's what we are having in this condition. So what does this tell us? Number one message we can deduce from this. Number one message is that if we have the graph this way, okay, the graph does not cut across the origin. The graph cuts across somewhere around the positive side of the y-axis. And that is the reason why we are having a positive c. Okay? But the graph has a negative slope. It has a negative slope. So having a negative slope means the graph slopes downward. It slopes from up towards the down direction. So that is another thing again about this, which means the graph of t squared against h, the graph of t squared against h is a graph with negative slope. It slopes downward. It has an intercept on the y-axis, and it's a positive intercept. Okay. So if we want to have a rough sketch of the graph is going to be like t squared, graph of t squared in second squared, okay, against the height of the room in meters. Okay. If it was in centimeters, you can be in centimeters during the experiment, but when you are doing your calculation, okay, especially when you want to find acceleration due to gravity with this you have to change it, you have to convert it to meters. It may be centimeters in the experiment, but whatever value you used during the course of the experiment is the unit that you apply here. Okay, so we have the origin 0. So it means that from the way we see, from the structure of the equation, we see that it is a graph that slopes downward and that has an intercept. The value of the intercept of the graph, is what this represents, which is 4 pi squared h over g. Okay, that's what it represents. And then it slopes downward, which means we have a negative slope. And then it also shows that the slope of the graph, okay, the slope of the graph is equal to 4 pi squared over g. So which means if I plot this graph, if I actually plot this graph and I get the value of the slope, okay, if I plot this graph, I obtain the slope of the graph. Whatever result I get as the result of the slope, I will insert it into this equation, okay, or I will equate it to 4 pi squared over g, and then from there, I'm going to get the value of the slope and the value of the acceleration due to gravity. For instance, let's assume that you got the slope as, definitely going to be a negative slope. So minus 0.04 as the slope. That's what you got after plotting the graph and looking for 2 points across the graph. You develop the slope triangle. You look for change in h, okay, and then change in t squared, okay, and then you plot the graph. You do t squared 2 minus t squared 1 over h2 minus h1, and then you did all of those things and you got a particular value. Definitely the value is going to be a negative value, okay, because whatever we see here has shown us that the slope is negative. So whatever value you now get, equate it to minus 4 pi squared over g. Okay, so minus cancels minus, then you cross multiply, which means 0.04 g is equal to 4 pi squared. And so g, acceleration due to gravity, will be equal to 4 pi squared divided by whatever is it that you got as your slope. I'm just using this. This is the value you're most likely going to get anyway. So, but whatever is it that you get, you put it here, okay? So, let me just put something general. So, which means the acceleration due to gravity is 4 pi squared divided by the slope. 4 pi squared divided by the slope. Anything you get for the slope, okay, you slot it into this place, you get the value for acceleration due to gravity. Okay, so that is that as per that for this particular experiment. So we discovered that, we derived that the graph of t squared against h is a negative, it has a negative slope. That's number one. Number two, we discovered that the intercept on the y, it has an intercept which is equivalent to what? 4 pi squared, the height of the room over g. So which means if you want to calculate the height of the room using this experiment, you can easily calculate the height of the room. What you do is you equate, you first find the acceleration due to gravity, okay, using the slope. When you get the acceleration due to gravity using the slope, equate it into this place. So slot it into this place, the value of g. You have the 4 pi squared, then you find h. You now equate the intercept, whatever is it as that you have here as a value on the y-axis, which is on the t squared axis. That is the intercept. So whatever is it that you get, you equate it to 4 pi squared h over g. You cross multiply, make h the subject of the formula, and then you are going to get the value of the height of the room. So which means the height of the room can be obtained from the intercept of the graph. The gradient or the acceleration due to gravity, can be obtained with the help of the gradient. Okay, the height of the room can be obtained with the help of the intercept, and then the graph slopes downward, and different properties. Okay, we are going to solve a couple of questions after all of this. So we are going to solve a couple of questions that test your knowledge of all these things. So you will see where all of these things that I'm explaining, where they do apply. So I just believe that you've gotten to understand how we converted the nonlinear equation into a linear equation and also made some important deductions from that linear equation. As a matter of fact, we even used all our deductions. We used a part of it, which is this loop, to find the acceleration due to gravity. And then we also use a part of it, which is the intercept, to be able to determine the height of the room. Okay? And then that is that as per that. So it's just a very interesting something. I hope you understood. If you don't really understand, you can slow down the video because I'm trying to talk very fast. I'm teaching very fast because I don't want the video to be long. So, but you can always slow it down or you can fast forward it. Okay, if I'm too slow for you, you can fast forward it. If I'm too fast for you, you can slow down the video. And if you have any question despite all of this explanation, and if there is anything that is not really so clear to you, don't worry about that, okay? Just reach out to me through the contact that is flashing on the screen, and then we'll get to talk. Okay, so we've come to an end of this particular section in which we try to find the acceleration due to gravity using a simple pendulum hung from an inaccessible height. We've also been able to make important deduction, and we also learned how to convert the nonlinear equation into linear equation. So we have learned, and then I'm going to see you in the next video. In the next video, we'll be discussing something similar to this, but that time, in that case, we are not dealing with the simple pendulum experiment. We are rather dealing with a mass that is hung on a string. Okay, see you there. Bye.